Many chemistry students confuse molecules and compounds, and it is easy to see why. If you take the definitions of the two, you'll see a lot of the same concepts. Their definitions share more than they differ, but in chemistry, the differences matter. Get it? Matter and chemistry. Okay, moving on. Let's start by defining what a molecule is. When two or more elements chemically bond, this is known as a molecule. Molecules can be stable or unstable, and they can also be heteronuclear or homonuclear. Homonuclear molecules are made up of two or more atoms of the same element. For example, H2, or hydrogen, with 2 atoms of hydrogen. P4 with 4 atoms of phosphorus, and N2 with 2 atoms of nitrogen. These are homonuclear molecules. By contrast, heteronuclear molecules consist of several elements, like CO, or carbon monoxide, with 1 atom of carbon and 1 atom of oxygen, or water, or H2O, with 2 hydrogens and 1 oxygen. Now, time for us to look at compounds. A compound is a substance made up of many identical molecules composed of atoms from more than one element held together by chemical bonds. Since they have a physical form continually visible to the naked eye, compounds are always stable. Every compound is a molecule, but not every molecule is a compound. Confused? Well, let's look at some examples. Water is considered both a molecule and a compound, and that is because 2 or more atoms are bonded together, 3 atoms are bonded, so it meets the requirements for being a molecule. Water molecules consist of different elements bonded together, hydrogen and oxygen, and water molecules can coexist to form that liquid that we so depend on, with the same name, water. And between those water molecules, some chemical bonds and interactions are happening, making it a stable substance. And that is what we call a compound, everyone. H2O is the smallest configuration of bonded atoms that still retain water's chemical composition. Now we're going to look at phosphorus, or P4. P4 is a molecule, but not a compound. Because 2 or more atoms are bonded, 4 atoms are present, so it can be classed as a molecule. The atoms belong to the same element, all 4 atoms are phosphorus, so it cannot be considered a compound. Molecules exist at the atomic level, so they cannot be seen with the human eye. Compounds, however, are easily visible with their physical form. You know how much salt you're putting on your food because you can see the compound sodium chloride pouring out of the salt shaker. But if one day you're sitting around bored and decide to launch yourself into the upper atmosphere of the Earth, you might spot the Great Pyramids of Giza, but you won't see ozone or O3 molecules even if you're floating amongst them. In molecules and compounds, atoms are held together through different types of atomic bonding. Atomic bonding is similar to other types of bonding. Growing up, all you want is stability. A roof over your head, bills paid, and good food. Atoms are the same. Atoms want to achieve a stable, low-energy state, and if bonding with other atoms gets them to that state, then they'll do it. If you're in a high-stress state because you've got exams coming up, you might bond with your favorite Netflix show to lower your stress level and become more stable. Let's say that it works similarly for atoms. There are 2 types of atomic bonds that we need to learn: covalent and ionic. First, we'll take a look at covalent bonds. Covalent bonds form between 2 nonmetals with similar electronegativities. Covalent bonds are also significantly more common in organic chemistry than ionic bonds. Let's look at hydrogen for an example of how covalent bonding works. A hydrogen atom has one proton with a positive charge and one electron with a negative charge. When two hydrogen atoms meet, first, like every polite atom, they say,
"Hello, how do you do, sir?"
Then the nucleus, which is made up of protons of each atom, is attracted to the other atom's electron. However, neither atom is powerful enough to steal the electrons from the passing hydrogen because they have low polarity, or similar electronegativities. So instead, they share the electrons in their outer shells, creating a stable H2 molecule. H2 is an example of a simple covalent bond where each atom provides one electron to the bond. However, other types of covalent bonds exist too. A coordinate or dative covalent bond forms when one atom supplies both electrons in the bond. An example of this is ammonium ion, NH4+. Ammonia, or NH3, has a pair of unbonded electrons, but it will bond with hydrogen to create NH4+ if the hydrogen atom leaves its poor one electron behind. How selfish of ammonia. In this covalent bond, both electrons come from the nitrogen atom and the hydrogen just brings its proton. After the bonding takes place, coordinate covalent bonds are no stronger or weaker than a traditional covalent bond. Another type of covalent bonding is polar covalent bonds. This is where one atom in the bond is more electronegative than the other, creating a greater attraction. And this results in the electrons being unequally shared. An example of a polar covalent bond is the hydrogen fluoride, or HF molecule. The fluorine atom is more electronegative, so the electrons stay closer to the F than the H, although they are still shared. Now let's talk about ionic bonds. Ionic bonds form between a metal and a non-metal, where there is a high polarity between the elements. In this bond, there is a complete transfer of electrons between the atoms. The metal atom loses its electrons to become positively charged. We call this a cation. The non-metal atom receives the electrons from the metal, becoming a negatively charged anion. Ionic bonding happens because metals characteristically have few electrons in their outer shells. If a metal wants to achieve a more stable state, it can unload these electrons to a non-metal that wants them, thereby achieving noble gas configuration, which is a very stable state. Ionic bonds are much stronger than covalent bonds and take a lot of energy to break down. Now, what are polar and non-polar molecules? In chemistry, polarity is the distribution of electric charge, whether between individual atoms or entire molecules. Imagine polar magnets with two different poles. Some molecules have different polarities on the same molecule. One part of the molecule is more negatively charged and therefore attracted to positively charged parts of other molecules, or vice versa. Some molecules have equal distribution of charges throughout its atoms, so they have no polarity. They can't be attracted to other molecules. They're just not into any sort of relationships and want to be left alone. All molecules exist on a spectrum of polarity, with some molecules being highly polar or clearly nonpolar. A completely polar bond is an ionic bond, and we would typically refer to them solely by this definition. We wouldn't say a non-polar ionic bond. All ionic bonds involve polarity. When it comes to covalent bonds, there is more of a spectrum. Some covalent bonds are nonpolar, like the homonuclear diatomic molecules N2 or nitrogen, O2 or oxygen, or Cl2 or chlorine. Others are decidedly polar, like sulfur dioxide, SO2, water, H2O, even ammonia, NH3. So how do chemists decide what falls into each category? If the atoms in the covalent bond have an electronegativity difference lower than 0.4, they are considered nonpolar. But if the difference falls between 0.5 and 2.0, they're polar. Anything greater than 2.0 would be an ionic bond. Now a moment to geek out. Do you have a favorite molecule? If so, let me know which one and why in the comments below. Like this video so I know you want to see more of these in the future, and subscribe to my channel if you want to keep track of what is coming up in the near future. I will see you in the next video.